Looking at a quadratic example here, finding this inverse is the same process we've used for a while. F of x is the same thing as y, so we're going to start by switching our x's and y's. The goal is to get y by itself, so a bit of algebra 1 comes into play here, adding 4 to both sides. Keep in mind, x and 4 are not like terms, so x plus 4 is just x plus 4. Now, in order to get that square out of there, we would need to take a square root. Where we need to be careful is when we take the square root of both sides of an equation, there are two possible cases. When you think about whole numbers, for example, if I were to take the square root of 16, there are actually two answers. 4, because 4 times 4 is 16, but also negative 4, because negative 4 times negative 4 is 16. So when we take a square root in our algebra, we do introduce that plus minus. So unfortunately, this inverse isn't a function, but that's okay, we can still graph it. I'm going to go ahead and commit a cardinal sin and write that inverse as f inverse of negative 1. Despite the fact that it is not a function, it is still something we can graph. So we'll start with the parabola. Graph that parabola in blue. It's been a while since we graphed any quadratic equations, but note that what we're looking at here, x squared minus 4, well, that's something that, if we let x be 0, we could have a 0 minus 4, which is just the point 0, negative 4. Or it's something maybe you recognize the difference of squares. And that can help you find zeros of the polynomial. One would be a positive 2 and one would be a negative 2. Or barring that, if you don't recognize any of those things, you could make a t-chart, plug in some values and see what you get. I'll do that over here. So if I substituted 1, for example, 1 squared is just 1. Take away 4 gets me negative 3. So we know 1, negative 3 is on that parabola. Or I could substitute in negative 1. Negative 1 squared is still 1. Minus 4 is negative 3. Or, you could always just use your calculator. We all have graphing calculators, so you can use that y equals option to get a few points that way. However you choose to get points, again, I know we haven't used a whole lot of quadratic graphs recently. But however you need to find those points, go for it. Feel free. Once you have some points, go ahead and connect them with a nice pretty U. And now we can focus on the inverse. So note that the inverse has this plus minus business. What that means is I actually have two things I need to graph. The positive square root of x plus 4 and the negative square root of x plus 4. You can think about that as a radical function that's been shifted to the left 4 units. These we just graphed. So hopefully this shape is a bit more fresh in our minds if the quadratic wasn't quite something we were comfortable seeing again. We did just play with these radical graphs. So we're going to shift 1 to the left 4 units. So the starting point will be here, and I'll start with the positive 1. From that start point, we can go up 1 and to the right 1, then up 1 to the right 3, and then up 1 to the right 5, and so on. That's the positive radical function. The negative one will just be a reflection of that. So we'll have that same point at negative 4, 0. There'll be a point down 1 and to the right 1. Down 1 and to the right 3, down 1 and to the right 5, so on and so forth. And if you look at this, this graph, it's a bit messy, but we do have two graphs. We have our parabola and our doubled up radicals there. And if we're like, I wonder if I did this inverse thing correctly, we can once again double check that there is a reflection. That is not a line tool. Take 2. We can double check that that is a reflection over the line y equals x. It's a bit messier here, but you want to double check that your points are all reflections. Some of them are quick and easy to find. There's one there. You can look at the vertices here. There's a reflection there. Likewise, we've got this point here, reflects down to that point there, so on and so forth. So more going on, but still something that we can double check. Just as a heads up and as a bonus example, you could do the same thing with cubics. Let's say we had like y equals x cubed, for example. If we wanted to find the inverse, we could switch it and make it x equals y cubed. In order to get rid of that cube, we could take a cube root. So this would be our function, and this would be our inverse. And graphing those, it's been a real long time since we graphed cubics, but roughly our function would look like that. And our inverse, well, our inverse is just one of those cubic graphs that we made not too long ago, which looks something like this. My picture isn't super beautiful, but you can see that we have that reflection we expect over y equals x. So we can graph all kinds of functions and their inverses to see that relationship. This is one of those units where I recommend maybe heading over to Desmos, plotting a few from previous homework assignments to see what they look like, checking their inverses, and actually seeing for yourself that yes, you did the algebra right. Again, this is something that you can do to check your work. You can also use function composition to check your work. So there's a lot of options when it comes to inverses. So this is the last section for this chapter. Let me know what questions you have. There'll be a review coming around shortly. Good luck. Have fun.